Welcome back. Today we're going to continue our topic from the last lesson, which is about chemical reactions. And this is the material which is included in chapter 10 at various points. And there are a variety of topics I want to talk to you about today. One of them is solubility, which is how different substances dissolve in water to varying degrees. We'll talk about the relative activity of metals and halogens, and we'll finish off our lesson on reduction reactions, which are reactions that involve the transfer of electrons during the reaction. And some of the reaction types that I talked to you about in the last lesson are also redox reactions. So it's another way of classifying reactions and can be very useful. So before we get started, I'm going to talk to you a little bit about the properties of water, because water is going to be important for us to understand solubility, since we're going to be talking about substances that are dissolved in water. And water is a very unusual chemical compared to other chemicals that are similar in its size and shape. And one of the things we need to think about is what its molecular geometry is. So from the last couple lessons, we talked about molecular geometries, and water has the shape of a bent molecule because it has two lone pairs, and its lone pairs affect the geometry such that instead of being linear, it's bent. And due to the strength of a hydrogen-oxygen bond, water also has the property of it being having hydrogen bonds. And so if there are other molecules of water near water, it will intermolecularly bond with water such that there is a force of attraction. And what we can see from this kind of unusually drawn structure of water is that I have the positive charges where the hydrogens are, and the negative charges where the lone pairs would be. And we can't see lone pairs, so they're not drawn in here. And then our bond dipole is going to go from the positive charge through the molecule towards the negative charge, so that every water molecule, when it's in solution, will want to orient itself such that their dipoles are aligned. You have the positive to the negative, and so on. So if I were to draw another water molecule here, well, let's draw it this way. So I'll switch over to blue, and we'll draw some water molecules up here, and we'll put the lone pairs like that. And if there's another water molecule nearby, it's going to want a hydrogen bond. And since water has two lone pairs, it can be donating those lone pairs into hydrogen bonds for two water molecules. And then its hydrogens can accept the lone pair from two other water molecules, so that each water molecule can be surrounded by up to 4 water molecules. And all the water molecules I have drawn so that their dipoles are also aligned. And this provides a great degree of stability for water, so that it changes its physical properties from other molecules. So for its size, you typically expect water to have a boiling point around negative 100 degrees Celsius, but it's 200 degrees above that. It's 100 degrees Celsius. And similarly, you'd expect that its freezing point would be somewhere around negative 120 degrees Celsius, but it's 0 degrees Celsius. So there's a large increase in both the freezing point and boiling point of water, and that's due to its hydrogen bonding. Another interesting thing about water is it has a high cohesion, and this allows trees and other plants to pump water from the soil to a great height. So that's an interesting property of water. And then I already talked here about the hydrogen bonding. But one thing to point out is that there is a difference between the hydrogen bonding in liquid water and solid water, also known as ice. And when you get to a solid form of water, we end up having around 4 hydrogen bonds per water molecule. Whereas in liquid water, the water molecules are moving around more, so you have less hydrogen bonding. You have around 3 in bulk water. And this results in the density of ice actually being less than the density of water. Around 0 degrees Celsius, during that phase transition from liquid water to solid water, the density drops from around 1 gram per milliliter to around 0.9 grams per milliliter. And that's because there's more hydrogen bonds, more structure, and a larger mass per volume. A smaller amount of mass per volume, because the volume of those water molecules and the waters around it, which are called the sphere of hydration, that ends up increasing the volume. So the density ends up dropping for ice. And last fact about water is it's the universal solvent for life, as we know. Our body contains around 70% water by mass. And this does change, depending on what cell type we're talking about. Bones and fat cells have the least amount of water, but still around 30% water by mass. And this is really important to think about in terms of chemistry, because there's always going to be water present during a reaction in the body. So when we're doing biochemistry, we need to think about water all the time. We can't just ignore it. It's one of those things we put in the back of our mind. But for today's lesson, we'll be constantly thinking about water's involvement in the reaction. So let's jump to the next topic, which is solubility. And solubility, by definition, is the amount of substance that can be dissolved in water. And so if I look at this packet of sodium chloride that's being poured into some pure water here, we can define the smaller substance, the thing that's being dissolved, as the solute, and the portion that the solute is being dissolved in as the solvent. So here's the solute, the NaCl, and the solvent, which is water, and will almost always be water in chemistry, unless there are some other solvents that we could think about as well too. And collectively, they're known as the solution. So the solution is the combination of the two. Now, what is happening at the molecular level? Because when we look at this from a macroscopic level, it doesn't look as if the sodium chloride, initially it takes a second to dissolve, but if you add just a small amount, it'll mix with the water, and then it will look as if there's just water in there. You can't really see the salt anymore. But at a molecular level, what's occurring during that dissolution, during the stage at which it's dissolving, this sodium chloride crystal, which is an ionic matrix, has its ions pulled apart by the hydrogens or the lone pairs of the water molecule. So we can see, when I zoom in here, that the water molecule orients itself so that its lone pairs are towards the positive charges, which would be the sodium ions, or where its hydrogens, its partial positive side, is toward the anion, the chlorines. And so we end up getting these different hydration spheres around these ions. So the negatively charged ions, here being the chlorines, are surrounded by the number doesn't quite matter, but around 6 to 10 water molecules per ion. And you can see that the orientation is different for the positively charged, where the dipole is the other direction. And the first sphere of water molecules is the first sphere of hydration. There can also be a secondary sphere as well. And whenever these ions move in solution, they're moving with their water molecules. And it's improper to just think about these ions moving through solution. They're actually moving with the water molecules. That's a really interesting thing that we need to consider. Now, we can also write this in a different way. So let's go ahead and ignore what I just said, and we'll anytime we write Na plus in drawn here, we're going to assume there's water molecules around it here. And so if I put sodium chloride packet of it into the water here, there might be some amount that's at the bottom, and that's if you put a lot of sodium chloride in. It's not all going to dissolve. So the sodium chloride that doesn't dissolve will stay at the bottom, but the stuff that's in the solution will be mixed, and we'll get a bunch of ions of sodium and chlorine. In this depiction here, we have a saturated solution, which means that we've dissolved the maximum amount of solute for a particular temperature. And if we were to go and increase the temperature, this more sodium chloride would be able to dissolve, and we would end up getting an unsaturated solution, which is a solution that has less than the amount of solute needed for saturation. And again, the definition of solution is a solute dissolved in a solution, dissolved in a solvent. The dissolution equation is written where you have the solid ionic compound, and then on the right side of the arrow, you just break it up into its ions, sodium plus and chlorine minus. And you want to write the state of matter as being aqueous to show that this is being surrounded by the water molecules. That's what aqueous is referring to whenever we write that. Another way of writing this is the molecular equation, where we have the sodium chloride mixed with water to give us NaCl aqueous. There are different ways of writing approximately the same thing, but the dissolution equation allows us to see the ions that are separated. And in a lot of ways, this is a more accurate depiction of what happens because we're no longer having a solid sodium chloride matrix. So solubility is, again, let me kind of write this out. The amount of solute that can be dissolved in a given amount of solvent at a particular temperature. So when I look at how the solubility changes with temperature, we will note that for most solids, which are in this diagram on the left, that as we increase the temperature, the solubility in terms of grams of salt or grams of solute per 100 grams of solvent increase with temperature. The only exception here is cesium sulfate, which tends to decrease in solubility with temperature. It's a little interesting. But each of them changes with a different amount, right? So the slopes here tell us how much the solubility is going to change with temperature. Some start off high and increase it steadily. Some start off high and increase exponentially. Some start off kind of in the middle and increase very gradually. Like sodium chloride actually doesn't increase that much with temperature. At 0 degrees Celsius, we can only dissolve 35 grams, but at 100 degrees Celsius, we can dissolve up to 40 grams. So only a 10-gram difference, whereas the difference for potassium chlorate, KClO3, goes from 5 grams all the way up to 55 grams. So approximately a 10-fold increase rather than a 25% increase. So much, I guess that would be 550%. So much greater increase. Now, if we look at gases and how their solubility changes, it's actually directly opposite. So if I take a solution of oxygen, and I increase the temperature, the solubility, in terms here of millimolar, we'll talk about that in the next lesson, will decrease with temperature. And why is this? Well, it has to do with some information we'll learn at a later date, but with gases, the solubility is going to change, because when you increase the temperature, these gases will speed up, they'll go faster and faster, and this will allow them to overcome their vapor pressure and escape the solution. So the solubility ends up changing because of the kinetic energy that you're putting in. And so that is an interesting thing to keep in mind. It's also why during the summer months, there's less oxygen available in our lakes and rivers for the aquatic animals, and so it's something we need to monitor, especially in the really hot months like July. And then in cooler months, there's a lot more oxygen available for the fish. Now, opposite of temperature is pressure. So if I were to try to compress a liquid and use that to increase the solubility of a solid, it's actually not going to really change the solubility all that much. There may be a slight change, but for the most part, we're not going to look at that change. However, for gases, you can greatly affect the solubility by increasing the pressure. And this is something we're already familiar with. When we open up a can of soda, the pressure change when we pop the tab causes a sudden release of gases out of solution. So we store soda under pressure to increase the carbonation. So we want to dissolve more CO2 into the drink to give it its fizziness and its freshness. So we increase the pressure, and that'll cause more gas to be dissolved per unit of solvent. Okay, so we'll talk more about pressure in our gases chapter. Now, what I want to do is practice some of these dissolution equation examples, and they're all not all that hard to write. So for our first one, if I have potassium chloride and I dissolve it in water, we're going to have K plus ions, and we'll have chlorine minus anions. And remember, each of these is going to be surrounded by water molecules. And then if I take the salt calcium chloride and I put that into water, this will dissolve, giving us calcium 2 plus ions. And for each formula unit, 2 chlorine minus anions. So we do want to write these as if they're balanced. For potassium phosphate, we'll get 3 potassiums for each formula unit and 1 phosphate. And we want to remember that phosphates don't break up into phosphorus and oxygen. They stay as the polyatomic anion, which has a 3 minus charge. And then lastly, I have iron 3 nitrate. I know it's iron 3 nitrate because nitrate has a -1 charge. And we'll get an iron 3 plus ion and 3 nitrate anions. Okay, so that's how you can write a dissolution equation. Now, our next topic is to think about how we can predict the relative solubilities of different salts. So some salts have low solubility and they reach saturation very, very quickly. And this is shown in like a drop test where you have some amount of water and you put a small amount of that salt into the test tube. If you get a result like one of these 4, you know that you have fairly low solubility. And when you go on to take Chem 112, we'll talk about the quantitative amounts of the solubility. But for this class, we'll talk about the relative effects of solubility. And we can predict this using a set of solubility rules. The solubility rules come about from a study of the actual quantitative solubilities, but they're summarized here in a set of 6 rules that are applied in order. Here's our definition of solubility. It's the ability of a substance, the solute, to form a solution with a solvent. And that's going to be water in this case. So when we apply these general solubility rules for ionic compounds, we'll start with the first rule, is that most alkali metal salts and ammonium salts are soluble. So if I have any salt that has sodium, potassium, lithium, cesium, and I'm forgetting one. Let's look up our periodic table real quick. Rubidium. Although I'm not sure rubidium would be stable, but it could be. Or an ammonium salt, NH4+. So if we see any of those ions in an ionic compound, we're going to automatically assume that this is a soluble salt. Soluble enough that if I were to put a general, like if I were to put a favorable amount of salt in water, it would dissolve. The next rule is that most nitrates, acetates, and perchlorates are soluble. So nitrate is NO3-, acetate is C2H3O2-, and perchlorate is ClO4-. So if we see one of those, that's again going to be soluble. Now, once we get to rule 3, here I have 3 different metals. I have silver, lead, and mercury 1. When we have these salts, they're generally going to be insoluble. So silver is Ag+, lead is either 2+ or 4+, and then mercury 1 is, remember, a diatomic ion. It's interestingly, so it would look like Hg2 with a 2+ charge. So these salts are insoluble, and they'll come out of solution as a solid. And you can remember these are like pretty heavy metals, toxic, right? So any of these toxic metals are generally insoluble when they're mixed with something. Now, if they're mixed with a nitrate or a sodium, not sodium, but a nitrate or a perchlorate or an acetate, they will be soluble because that rule is above this other one. So you always want to apply these in order. And then we get on to the next one, which is the halogens, chloride, bromide, and iodide. So most of these, unless they're paired with silver, lead, or mercury, are going to be soluble. Also, there's a couple down here. Nope, that's it. And then you'll notice that fluorine is not listed. So fluorine has some different rules. We can look at this table down here to look at that. And lastly, we end up with these sets of rules, these carbonates, chromates, sulfides. So let me write all these out, and these are good to recognize. So carbonate is CO3 2-, chromate, CrO4, I think 2-. I got to kind of cheat there. Yeah, 2-. Sulfides are compounds with sulfur, oxides with oxygen, phosphates, and hydroxides. So a lot of these are insoluble, except when they're paired with, except for hydroxides of barium, calcium, and strontium, which are slightly soluble. So you can put a little bit amount of those in solution until they crash out. And then the last one is most sulfates are soluble. So if you get all the way down the table and you get down to here, we get to sulfate, which is SO4, 2-. Those are generally soluble unless it's calcium sulfate or barium sulfate, which are insoluble. So there's a lot of rules here, lots of exceptions here. And that's why it's helpful to have this handout available when you are working on a problem that involves solubility. And these will generally be problems that have double replacement reactions. This is another way of summarizing all these rules above, and you can simply look to find these ions. These are the always soluble ions. There's a couple that weren't mentioned above. We have chlorate and hydrogen carbonate. And then here's our generally soluble classes. The only added one here is fluorine. So fluorine will be soluble except with lead, calcium, barium, strontium, magnesium. And then sulfate is going to be soluble except with, I said calcium and barium, but also lead and strontium are listed here as well. And lastly, we have the generally insoluble classes. We have oxygen and hydroxide with their notable exceptions, and the other ones that I drew up above. There's another one here. This is C2O4. That's oxalate. So that's another one that can be insoluble. And then on the right here, I have our strong acids, which there are 8 of them, and our strong bases, which are the alkali hydroxides and the alkaline earth hydroxides, as well as thallium hydroxide, which somehow made itself on the list. And then I have the gases that form, just because it kind of, when we're working with double replacement reactions, we often want to refer to these gases that form. So here I'm going to go through several examples of solubility, and I'll draw out a molecular depiction and write out the formula for each of these. Well, the formulas are listed, so I'll just kind of draw out a depiction of these. So if I have silver chloride, which if we look at the rules from above, silver chloride is going to be insoluble because it has a silver ion. That's rule 3. So when I put this in solution, we'll get a mound of silver chloride. Now, even though a insoluble salt is insoluble, it will, to some extent, break apart into silver plus and chlorine minus. So we'll have just a few ions here of silver and chlorine. And we indicate this with a double-headed arrow, meaning that this reaction is in equilibrium. So it's dissolving, but then it's immediately reforming, and the equilibrium is in the direction of the solid, which is why we have so much of the solid here in this container. If I have a covalent substance that is polar, such as ethanol, even though it's not an ionic compound, it can still dissolve in solution. So it's not going to break apart into carbon, hydrogen, and oxygen ions, but rather it's just going to mix with the water. And one way that we can draw this is by simply just drawing ethanol here as, a circle, and I'm just drawing it here showing that the ethanol is mixed well with the water, which is that gray substance. And ethanol has a OH group on it. So what we're going to see is that there's going to be hydrogen bonding that occur between the ethanol and the water molecules, which is why this is so easily mixed. So anytime we have an OH group, unless it's a really long carbon chain, it's like a fat, it's generally going to dissolve. Here's another example of this. I have C12H22O11. This is sucrose. And it's not very apparent from this formula, but this sucrose molecule has a lot of OH groups. And so this will dissolve as well in solution. So we have 2 examples here of polar solutes. And when you have a polar solute and a polar solvent like water, they will mix together, and we call this a miscible solution. Now, how about if I put a nonpolar substance into water? Well, this will not lead to a mixing. So if I have this long carbon chain, C16H32O2, so only 2 oxygens here, this is a fatty acid. This fat won't dissolve. Instead, it will create 2 layers where I have the less dense substance on top and the more dense substance on the bottom. And so we'll have 2 layers here. So on the top, are we going to have the fat? And on the bottom, we'll just have the water here. So that's kind of like when we mix olive oil and vinegar, right? So vinegar is acetic acid in water, and olive oil is a fat. So when we mix those two together, you don't really get a good mixture unless you shake it very much, and it will create essentially like a micelle where you'll get somewhat of a mixing, but then over time it will separate out. So this you want to look at over time, and you'll see here that these are not very miscible compounds. Now, here's some examples of acids and bases, because we're going to be talking about these. If I have hydrochloric acid, which is hydrogen chloride in solution with water, this strong acid will break apart completely. So instead of having the molecule anymore, it's going to want to break up into its ions. And that's what's going to happen anytime that you have a strong acid or a strong base. It will break apart completely into H plus and the anion, or for a strong base, it'll break apart into the metal ion and hydroxide. For a weak acid, it will dissolve somewhat. Well, they'll all completely dissolve. They're already dissolved, but it will break apart somewhat. So we'll retain some of the hydrofluoric acid as HF. So some of it's not going to dissolve, but then some of it will. So we'll get kind of a mixture here. Like so. So when something dissolves really well, an acid dissolves really well, and it gives us H plus, and Cl gives us these ions. It doesn't have to be an acid, but any ionic compound that dissolves, or any acid that dissolves very well, is called a strong electrolyte, because this solution now can conduct a lot of electricity. Whereas this other solution over here has some ions, but not very much. And so when like around 1% of it dissolves, we call this a weak electrolyte. And the change is very rapid. And then there's also non-electrolytes. Those would be things that don't dissolve at all, like these polar substances up here, ethanol and sucrose. They don't actually dissolve, so these are non-electrolytes. Okay, so let's practice writing out some complete ionic and net ionic equations. And this is a little bit tricky. So what we're going to do here is we're going to start by writing out the double replacement reaction that we're already familiar with. And then we'll write out the equation as if it was all made up of ions. And additionally, we're going to have to predict the solubility here. So we're going to have to look to see which of the two compounds here in this double replacement reaction is insoluble. And we'll make use of these solubility rules here to predict that. All right, so when we put potassium chloride in solution with sodium sulfide, both of which are soluble compounds, we end up getting the exchange of the cations. So sodium will pair with chlorine, and potassium will pair with sulfur. So we'll get sodium and chlorine that come together to give us sodium chloride. And then we'll get the the potassium and the sulfur that come together is potassium sulfide. Now, both of these are going to be aqueous compounds. So in this sense, we actually don't have a visible reaction. So we're only going to be able to, in the lab, notice a reaction if there's some compound that comes out as a solid, or there's a color change. And so in this case, we're actually not going to be able to observe this, but nonetheless, let's write out the complete ionic equation. So this is just the molecular equation. And then if I were to think about, well, in actuality, potassium chloride is K plus and chlorine minus. So I'm going to break apart each of these into its respective ions, and we're going to pay attention to how many of them there are as well. And I'm going to write aqueous for all these to remind us again that these ions are surrounded by water. Okay, and then one thing I just noticed while I was writing this is I didn't balance the reaction above. And so what we need to do is make sure that this equation is balanced before we do this. 2KCl, because we, and then 2 sodium chloride, so that's all balanced. So I'm going to go ahead and fix the balancing here. So there's 2 of these, 2 of those, 2 of these, 2 of those, and 2 of these. All right, and what I'll do is I'm going to underline all the same ones on both sides. Use different color for each of these. And we will see that we have the same entities on both sides. So when this happens, we can't simplify the reaction any further. This is known as a complete ionic equation. And then this is just our molecular equation. So we're not breaking it up into the ions. And then in this example, because there's no solid, no solid product or insoluble product, we're not going to be able to write a net ionic equation. Or you could, I guess, there's okay. Now moving on, let's go ahead and look at one that we can write one for. If I look at the reaction between silver nitrate and potassium sulfide, yep, that's going to work. We will be able to exchange the potassium and the silver. And when we do this, we'll get potassium nitrate, which is KNO3. And let me leave out the solubilities here for a second. And then we'll have silver sulfide. And remember, silver is always a 1+ charge. You can always look back at your periodic chart of the ions to figure that out. So then we'll get silver sulfide Ag2S. And we want to predict the solubilities here. So if I go back up at my solubility rules, And we say, well, most alkali metal salts, something that includes potassium, is going to be soluble. So the potassium nitrate is soluble based off the first rule, and it's also based off the second rule, because most nitrates are also soluble. So we could say it's very, very soluble. However, the next one, we're looking at silver sulfide. And so sulfides show up down here in rule 5, and silver shows up here in rule 3. So we look at rule 3 and say most silver salts are insoluble. So here we can see that this is insoluble, so we're going to write S for solid. And then this will stay soluble, so we'll write AQ for aqueous. That can be a little tricky because we might be thinking S means soluble, but S means solid here. And then lastly, we want to balance this reaction. And we'll put a 2 here and a 2 here. Okay, so let's go ahead and write the complete ionic equation. I'll just write the coefficients in black here. So 2Ag plus and 2 nitrates Okay, making our way there. Always want to remember the charges and the states of matter. It gets pretty cumbersome. Now, once we get to the last part, this is our solid. So this is not going to break up. It's going to be at the bottom of the container, and we'll just write it as Ag2S solid here at the end. So when I go through and I look at both sides of the equation, we're going to have a situation where some things are on both sides, but other things are only on one side. Okay, do the rainbow here for this one. Okay, so then when we look at this, we can see that the complete ionic equation has nitrate on both sides. So those actually kind of cancel each other out. And as well as the potassiums on both sides, these cancel each other out. So the potassium and nitrate are known as spectator ions. They're important in the reaction, but we don't notice any change in their state. They stay aqueous throughout the experiment. And when we go to write the net ionic equation, what we want to look at is just the chemistry that's occurring here. So we'll write the net ionic equation as just the things that did not get canceled out. That ends up being the things that make up the solid. So you don't actually have to write the complete ionic equation to find the net ionic equation if you recognize that fact, that it's only the things that will make up the solid that are on the left and the solid itself that's on the right. So that's known again as the net ionic equation. And net ionic equations are really helpful to write out when we're studying oxidation reduction chemistry, which we'll talk about in just a minute. So we'll be able to look at how we're going to be able to look at this and see a lot easier how electrons are being exchanged, if at all, in these reactions. All right. Now for this next one, definitely you should practice this on your own first. And so pause the video and see if you can write the molecular equation and then immediately write the net ionic equation. So just skip the complete ionic equation. See if you can write both of those. Okay, so let me try to write these out. I have lead nitrate and I have sodium carbonate. And we're just going to switch the cations and we'll end up getting sodium nitrate and lead 2 carbonate. So naming them is actually quite easy, but writing them can be a little bit trickier. So we'll start with sodium nitrate. And that's going to just be NaNO3. Now we don't want to just change the coefficients, exchange the subscripts over. We want to pay attention because note sodium nitrate is written like this. They're both a charge of 1. And sodium is an alkali metal. So right off the bat, we know that this is going to be soluble. Also, it's composed of a nitrate. So anytime we have a nitrate, that's soluble. So it must be then that the lead carbonate, the lead 2 carbonate, is our insoluble compound. It doesn't have to be. We have to go back and double check the rules. But lead carbonate is insoluble. If we go back up here, carbonates show up in rule 5 and lead shows up in rule 3. So lead is insoluble. And it's written as PbCO3 because the lead is going to stay in the 2+ state that is over here. And carbonate has a 2- charge. It's one of those that I always mix up. That's why it's important to kind of memorize these or have that chart available. And then that is our molecular equation. And if you were to write just the net ionic equation, we're going to look at this portion here, and we'll look at the things that make it up. So it's made up of lead, and it's made up of carbonate. So other thing I didn't balance this, so we should balance this reaction. We need 2 sodiums and 2 nitrates, and then that's good. So we'll start by writing the lead portion, and that's going to be lead 2+. So if I have lead 2+ ions and there's carbonate ions available, they'll come together and they'll form this insoluble salt. That's lead carbonate. And there we have the net ionic equation. All right, cool. So now what do we do? Well, let's talk about the relative activities of different metals and the relative activity of different halogens. And I found this this graph here on active chemistry, and I kind of liked it. So when it says more easily oxidized, that's another way of saying more reactive. And the activity series for all the metals is listed here from the most active metal, which is lithium, which is our first alkali metal. And then at the very bottom is gold, which is very inert metal. So gold is characterized by its inability to react. And that's why it's used a lot in semiconductors, because we don't want it to react and be oxidized. We want it to stay inert. And then for the halogens, we'll see that the activity series is that fluorine is the most active. So if you can oxidize substances where you just pour spraying fluorine gas on it, and it will just combust. It's really interesting. And then that activity series goes down as you go down the periodic table. So iodine is the least active halogen. And there is a way to kind of memorize these. As we go right on the periodic table, the metals become less active. And as you go down the periodic table, they become less active as well. So we'll see that lithium is followed by potassium, which is right below it on the periodic table, skipping sodium here. And then, where is sodium? It didn't make it. And then we have barium, calcium. Oh, there it is. Sodium's right there. Just skipped over it with my eyes. So it's not a perfect trend, but some of these metals, when they're very active, they're at the top of this activity series. They will react directly with water to form hydrogen gas, and they'll also directly react with acids as well. Whereas some of the metals that are in the middle of the series, they'll react with acids but not with water. And then as you get down into the further series, they'll react with strong acids but not water, or not with acids at all. And so your textbook talks a little bit more about the activity in terms of that regard. What I want to look at here is 4 different chemical reactions to predict whether these reactions will actually occur or not. And for them to occur, the metal that is trying to replace the other metal needs to be more active, or the halogen needs to be more active. So when I look at the reaction between zinc and mercury 2 chloride, we see that zinc is trying to replace mercury here. And what we look for is the relative activities, and mercury is all the way down here. So since zinc is higher up on this activity series, it will displace the mercury. So we end up getting a reaction that occurs, and we'll write mercury. That's going to be a liquid. Mercury is always a liquid at room temperature. And then we'll get zinc chloride. And zinc chloride, I guess we don't know whether it's aqueous or not just from looking at it. But we could look at the solubility rules and say, well, most chlorides are soluble. And I don't see zinc listed here at all. So I'm going to assume that it is soluble. And so that's kind of how we can make also use of the solubility rules. Now, if I look at the next example, here I have zinc again, but we have calcium. And calcium is a more active metal. So you cannot replace a more active metal with a less active metal with a more active. You can't replace a more active metal with a less active metal. Okay. So NR stands here for no reaction. Now, it might occur to a small extent, but we're going to predict just from this trend that it won't happen. Now, in these next 2 examples, I have halogens, and for halogen replacements, the halogens switch places. So here we're trying to replace this, that doesn't work. Here we're trying to replace this, and bromine and iodine are here and here. So bromine is a more active halogen, so it will be able to displace the iodine. So here this reaction does occur, and I'll write the iodine first. Here iodine could be a solid at room temperature, or it could stay in solution. And then the calcium bromide would be CaBr2. We're again going to assume that is aqueous. From our rules up above, we don't see bromine and calcium listed in that same group there. However, when we try to do this one, this doesn't work. Kind of like how this other one didn't work. Because chlorine is a more active halogen, and we're trying to displace a more active halogen with one that's less active. So this does not work for the same reason above. So chlorine is more active than bromine. And now you know a little bit more about how to predict whether a reaction will occur or not. And you need to know these relative activities. There's also these oxidation half reactions here that are listed. And we don't need to be paying attention to this at this moment. It just shows that if I were to have lithium and it were to be oxidized, it would lose an electron. It would break apart into lithium plus and a free electron. So these are just the oxidation half reactions, which we're not going to learn about half reactions until Chem 112. But we are going to talk about oxidation reduction full reactions, and that's the last part of this lesson. And so if you're reading chapter 10, you'll find this at the end. And most of the reactions that we've already examined in the last lesson can be classified as oxidation reduction reactions. These are reactions that are classified on the basis of a transfer of electrons between species. So the transfer of electrons. The atom that loses electrons during a transfer is referred to as the one that's oxidized. And so this is a definition. So if you lose electrons, that atom becomes oxidized, whereas the atom that gains electrons is reduced. So if we were thinking about some of the ions that we're already familiar with, if we have a metal and that metal loses electrons, it becomes oxidized. So calcium becomes calcium 2+, that's an oxidation. If I have an atom such as oxygen that gains 2 electrons so that it can be having a full octet, that would be a reduction because it's gained 2 electrons in that process. Now, we can also refer to the species that's oxidized and the species that's reduced, rather than just the atom. So if we look at the reaction as a whole, that's not just the atom, but the entire species, we can refer to the oxidized species, the one that contains the atom that's reduced, as the reducing agent, because it supplies the electrons to the other one. I think I might have misspoken. So let's go through a couple examples, and I'll look back at this chart here. But to determine, first off, which atom is oxidized and which one's reduced, we need to assign an oxidation number to the elements. And the oxidation number, or the oxidation state, is something that's a little bit different than the formal charge. Formal charge, if you remember, helped us determine whether a atom was charged or not. But the oxidation number helps us determine how many electrons that atom has, and it imparts the electronegativity as well. There are a couple of rules that we can follow that make this easy. So elements that have an oxidation state of 0, all elements have an oxidation state of 0. So if I have oxygen, which is a diatomic element, or gold or bromine, which is also another diatomic, by definition, all of these elements, the oxygens in this molecule, are going to have 0 oxidation states because the electrons are being shared between the oxygens, so there is no electronegativity difference. So there's 0. Whereas ionic compounds, they can be broken up into their ions, and if it's a monoatomic ion that we're looking at, such as potassium, those ions take the oxidation state of their charge. So we'll write +1 for potassium and +3 for a chromium that has a 3+ charge. Whereas if that ionic compound contains a polyatomic ion, we might need to use a little bit of algebra to figure out what the oxidation state of the atoms in that polyatomic ion are. So let's go through a couple of examples of this. And also, what we'll need to do for this is we're going to need to give any, because most polyatomic ions contain oxygen and hydrogen, we'll give oxygen the state of -2 and hydrogen the state of +1. So if we're looking at the chromate anion, CrO4 2-, to find the oxidation state of chromium, we'll set up an algebraic equation where X represents the oxidation state of chromium, and each of the oxygens has a -2 oxidation state. Not a -2 charge, but an oxidation state of -2. And then we'll set that equal to the charge of the polyatomic, which is -2 in this case. So here I have an equation that's X plus -8 equals -2. If we add 8 to both sides, we'll find that the oxidation state of chromium is +6. So we can find oxidation states this way. And what we're going to then look at is how that oxidation state changes over the course of the reaction from the left to the right side. So what we want to do for these examples is find the oxidized atom, find the reduced atom, and we'll also talk about the oxidizing agent and reducing agent. And I want to know what the total number of electrons that are transferred are. So to start off with this one, we have calcium and chlorine, which are both elements. So these are going to have oxidation states that are 0. And what I like to do is write one of them above and one of them below. And then on the right side, we'll see that the calcium and the chlorine, they form a compound. So this is a combination reaction. And the calcium now has a +2 charge because in calcium chloride, it's a ionic compound. And we're going to think about them as if they are their ionic forms. So calcium is Ca2+, and chlorine is got a -1 charge per chlorine. So we're looking at this on a single chlorine basis. So right here we'll write -1. And then what we want to look at is how do these change from here to here. So on this side, we see that this one gains a charge of +2. So what's happening here is it's actually losing electrons. So it loses electrons. So therefore, this is oxidized. And one way to remember this is from this acronym that I've used for a long time. It's Leo, the lion, says grr. So grr spelled G-E-R. So Leo says grr. That is one way of remembering. Let me put this in capitals. That if you lose electrons, then you're oxidized. But if you gain electrons, you're reduced. So here we're losing 2 electrons. That's why we get a positive charge. It's opposite from what we might think. And then in this one, we are gaining electrons. So therefore, this chlorine atom is reduced. So what is the oxidized atom? What is the reduced atom? So we just said this. The oxidized atom is the calcium. the reduced atom well, this one here is the chlorine. It's going to gain electrons. So we want to look at it from a left to the right side. Now, this term gets thrown around a lot, oxidizing agent. So let's look back at here. And I don't know if I wrote this right. So the reduced species is the oxidizing agent. The reduced species here is the chlorine. And it's so the reduced so it's known as the oxidizing agent because it is the thing to receive the electrons. So it oxidizes basically the other thing. So the reduced species oxidizes the other thing. So it's referred to as the oxidizing agent. And what I will do is I'm going to write this as Ca and this is Cl. And we'll notice that these are opposites. So anything that has the reduced atom is the oxidizing species. That's Cl2. So it refers to the whole molecule. And then the reducing species. Oh, well, actually not species. We'll just say agent. I like that word better. Reducing agent. That's the thing that gets reduced. No. That's the species that it's hard to explain. That supplies the electrons. So you can kind of look at this rule. So here, the reducing agent contains the atom that's oxidized, contains the atom whose ionic charge increases. It's the electron donor. So it provides the electrons. The other thing is what accepts the electrons. Okay. So here we have Ca. So it's the same. Okay, sorry, that's a bad explanation, but I think you'll get the hang of it. The total number of electrons that are transferred here, well, we want to look at just one side here. So the half reaction is essentially calcium goes to calcium 2+. And in the process here, it loses 2 electrons. So the total electrons that are transferred is actually 2. It's not 4. It's not 3. And that's because those 2 electrons that are transferred from the calcium go to the chlorine molecule, where one of the chlorines gets 1 electron, the other gets the other. So transferred is 2. I guess I said I wasn't going to talk to you about half reactions, but it kind of makes more sense if I do. So if I have calcium and it goes to calcium 2+ and 2 electrons, where we have chlorine plus 2 electrons goes to Cl2. Well, not Cl2, it's actually 2Cl-. So here we can easily see that 2 electrons get transferred, not 4, just the 2 here. So this would be the whoa, okay. Here's another oxidation reduction reaction. This is a combustion reaction for methane. And first off, is this balanced? It's not. So we're going to want to balance this reaction. We'll put a 2 there. And then what about the number of oxygens? We have to put a 2 here. 2, 4, 4. Okay, good. So in this situation, we're going to recognize on the left side that we have oxygen already, which is an element. So the oxygen here is going to stay as 0. It's got a +0 state. And then on the right side of the reaction, we have oxygen that is as part of the carbon dioxide and as part of the water. So this can be a little tricky to figure out what exactly is changing states here. So we'll look at the oxidation states of all of the atoms to help us out. Now for the carbon, we want to make use of the rule that hydrogen is going to get the state of +1. So we can do a little bit of algebra here where to find the oxidation state of the carbon. So the hydrogens are all going to be +1, but the carbons here are going to be x plus 1 times 4 equals the charge, and there's no charge here, so we said that equal to 0. So if each of the hydrogens has a +1 oxidation state, then when we solve for x, we find that it has to be -4. So this is the most reduced state of carbon when it has an oxidation state of -4. That's as reduced as it can be. So what we're going to have is the carbon is going to be oxidized. We know this is an oxidation reduction reaction because it's an oxidation. We have oxygen being added. So it does just make sense that this becomes more positive or more oxidized during the course of this reaction. In fact, it goes to its fully oxidized form, CO2. When we look at this, we have the oxygens, and I'll set up a different algebraic equation where, again, we're trying to solve for carbon's oxidation state. Each of the oxygens is going to have a -2 oxidation state, and then the charge on this molecule again is 0. So when I solve for this, should be 2 times -2. If I move -2 to the -4 to the other side, we end up getting that the carbon over here is +4. Okay, now how does the oxygens change? So each of the oxygens is going to be -2. So here we have this molecule, or this atom going from -4 to +4. This is an oxidation. And then we have the oxygen here going from +0 to -2. This is a reduction because we're gaining electrons. If we look at the water, we'll see that it doesn't change. So the oxygens over here are both -2, and then these hydrogens are +1. So the hydrogens here, they stay as +1 the whole time. So we don't need to worry about the oxidation state of, or the oxidation change of the hydrogens because they don't change. But yes, actually, we do need to look at this as well too. So, so some of the oxygens go here, and then some of them go over here. But either way, they're both -2 in these situations. So when I look at this reaction overall, and we think about the oxidized atom, we know here that it's the carbon, and the reduced atom, the one that gains electrons, is the oxygen. The reducing agent is the species that contains the oxidized atom. See, I think I got it now. It's one of the harder topics for me to explain, I guess, is the methane. So that's the thing that that contains the oxidized atom. And then the oxidizing agent is oxygen, of course. So this one makes sense. That's most of the time oxidizing reactions were named because of the presence of oxygen. Of course, there are other oxidizing agents. And then how many electrons are transferred here? What I like to do for this one is just look at the simplest case. So the methane goes from CH4 to CO2. There's only one carbon each. We get a total of 8 electrons that must be transferred here. In this reaction. So if I were to write out the half reactions, let's see if we can do this. CH4 goes to CO2. We end up losing 8 electrons in this process. And when we have 2 water molecules, they combine with 8 electrons to give, well, I actually don't know how to write this. Well, they combine to give us 1 CO2 molecule and 2 water molecules. And I'm not quite sure how to write that out, so I'm going to leave it out. But that's why we'll leave that to 112. I need to practice that some more, obviously. But let's look at this third example. See if we can get through this one. I have the permanganate ion, MnO4, which this compound is a very dark plum purple. It's very pretty. If I add in N2O3 to it and some acid, we can get an oxidation reduction reaction. And on the right side, we'll have Mn2 plus ions, nitrate, and H2O. So for this one, we're writing it without the ionic compounds present. So there are some other counter ions, but they're not important. So we're looking at just the net ionic equation here. So in this one, we'll look on the right side first and actually see that we have a monoatomic ion. It's Mn2 plus. So right off the bat, we know that this has got to be a +2 charge. And then on the left side, we'll have to figure out what the charge for manganese is. And we can set up our equation. So we'll set manganese to X, and then each of the oxygens will get a -2 oxidation state. We'll set it equal to the charge, which is -1. So this reduces down to X minus 8 equals -1. When we add 8 to both sides, we find the oxidation state for manganese to be +7. So what we can see is that we get a reduction here. We gain 5 electrons in this process per manganese. And then on the top, well, let's see what we have. We have oxygen, and oxygen we're going to pretty much ignore. It's always going to be -2 in these because it's not by itself. But then we could look at the nitrogen. And so the nitrogen changes. It's going to change states because there's 2 nitrogens here per 3 oxygens, whereas it's 1 per 3 oxygens here. So we'll need to find the oxidation states of each of these nitrogens. So for the left nitrogen, let's go and set, since there's 2 nitrogens here, we'll write 2x plus 3 times -2, and set that equal to the charge, which in this one it's 0. So when we simplify this, we get 2x minus 6 equals 0. 2x equals 6 when we add 6 to both sides, and then divide through by 2 to get x equals +3. So here we have this nitrogen having a +3 oxidation state. And then the nitrogen over here, we'll set that equation as x plus 3 times -2 and that one has a -1 charge. So x is equal to, we'll say x minus 6 equals -1, x equals +5. -1 plus 6 is +5. Okay. All right. So overall, we can figure out all this information again. Again, we don't need to look at the other atoms because they're all going to be like this hydrogen's +1 here. It's going to be +1 over here. The oxygens are all -2 on both sides. So let's look at how we can figure these information out. So the oxidized atom is going to be the nitrogen. So we can see here that it loses 2 electrons per nitrogen. The reducing agent would be that species right here, N2O3. And the reduced atom would be manganese. And then the oxidation agent is the MnO4-. So now if we want to look at how many electrons are being transferred, well, it's a little tricky. There are 4 MnO4- species here. And assuming this is correctly balanced, I don't think I double checked it, but it looks right. Let's see, we have 16 plus. 16. Oh, something seems off here. It's 31. And then the right side we have, yeah, that's balanced. So, and then on the right, so if we see that each manganese gains 5 electrons and there are 4 of them, then I would think that it would just be 4 times 5 or 20 electrons that are transferred here in this process. If we look at the nitrogens, we see that each nitrogen loses 2 electrons, and there are 10 of those nitrogens. So 2 times 10 is also 20. So 4 manganese go from +7 to a 2+ state like this. I'm not quite sure that's a proper way of writing it, but I'm going to do it that way. So we can see here we need 20 electrons to fully reduce the manganese to this 2+ state for this balanced reaction. And this is a tricky skill to learn, and that's why I want to introduce it in this class so that when you go on to take 112, you'll have some exposure to it. And I'm sorry if I explained that pretty poorly. I don't remember if the textbook talks about oxidation states. This might have been something that I added to chapter 10. You can go further in the textbook to find this information. But I think it's useful. And then on active chemistry, there will be a couple problems that you can practice to practice oxidation states and to see how electrons are transferred in reactions. These types of reactions are really useful for when we want to learn about electrochemistry later on down the road. Well, lots of information this past 2 days on chemical reactions, and again, don't get overwhelmed by it. Just practice being able to recognize the different reaction types. We'll see here that we have a synthesis reaction for example 1, and then example 2 is combustion. And then example 3, I don't exactly know how we would classify this other than a redox reaction. So this is why adding this other type of criteria of electrons being transferred is really helpful for chemists to discuss. And so now you know also a little bit more about solubility and how to predict solubility given these solubility rules. So make sure you print off a copy of it. There's a copy in the modules. And then a little bit more information about water too. That's kind of fun. So next lesson, we're going to talk about how to calculate chemical reactions that have limiting reactants. And then we'll talk about chemical calculations that are in solution. And so we'll be going back to our discussions on stoichiometry. So everything will be coming full circle now. So I look forward to talking to you about that in the next lesson, and hope you have a great day.